Alright, now this is what I'm talking about. The school year is almost over, the weather is beautiful, the sun is shining, there's almost nothing left to do. Oh, a piece of paper. I probably should read this. Oh no. AP Physics, group project, a lot of points, due Tuesday. Oh no. How am I going to do this? I don't remember anything from the class. Well, if I'm gonna make a lab, I have to do it on something that I know. But what? Kinematics. That's it. But what's a way where I can do kinematics and represent it in the easiest way possible? Interesting. You know, just about everything that has happened today has been really convenient. Maybe too convenient. Well, if this is for physics, I guess I'll do it. You know, I'm really sorry to tell you guys, but this is probably going to be the most boring AP Physics project ever done. I'm going to use my car to explain kinematics. Or rather, to explain how it's hiding them. Everyone, strap in your helmets. Behold, the greatest mode of transportation known to man, the Hobo Lightning. Here we are in all of its glory. An 8-wheeled contraption, powered by a battery, with lights and horns and a motor. It has many different features. This, everyone, is the Hobo Lightning.
Now with our experiment lies a practical goal. This is a realistic drawing of the Hobo Lightning, and as you can see, there are 3 wheels up front, 4 wheels in the middle, and a wheel in the back, which accounts for about 8 wheels. This is a very excellent machine, but it does have some flaws, one of them being that there's a lot of rolling resistance from all of these surfaces touching the ground. Our objective is to determine the U sub k, or the coefficient of friction, and see how that changes with weight. So the experiment was overall very simple to conduct and only had about 6 steps. The first one was to find the hill that we were going to use and to measure the angle of it. The one that we used specifically has an angle of 4 degrees, which we determined through a GPS app and also through a carpenter's level. The second step is to determine the weight of the cart and the 2 occupants on it. The dry weight of the cart, of it, along with 2 people on it, is 480 pounds, at least with the 2 people that we had riding on it specifically. The third step is to time how long it takes the cart to reach 10 miles an hour from a resting state. Of course, this is with no initial force put it horizontally, and is just to determine how gravity affects the horizontal movement of it, as you can see by that handy direction of motion arrow right there. The fourth step is to vary the weight put in the cart and to continue timing the acceleration from 0 to 10 miles an hour. Of course, we do that by placing salt bags, of course each one weighing 40 pounds, inside of the cart right there. Then all you have to do is divide each velocity by how long it takes to determine the acceleration with each weight on it, which is the 5th step. And the final step is to just plug in the acceleration and angle into the equation that we had in order to find u sub k. And it's just that simple. So as you can see here, I have reviewed our project data from each of our trials depending on the weight that we have put in the cart. This is how long it takes for the cart to get from 0 to 10 miles per hour. As you can see, for 0 salt bags, it's those 2 times, and for 1, it's those 2 times. And what I actually found impressive is it actually took less time for it to get from 0 to 10 with 1 salt bag than both times with 2 salt bags. So in the next video, I'm going to average all these times out for each amount of bags. So that way we can determine the average acceleration in each of these circumstances. So now you can see by simply adding the 2 times together for each trial, I was able to figure out the average times for each of the accelerations. See them right there. Might want to write them down. But yeah, that's just easy stuff. Just adding both the previous times together and dividing them by 2 in order to get those numbers. And that's what we'll use in our equation. Now, using some equations, we were able to determine our goal by starting out with F equals ma and then progressing from that to get an equation that we can use for friction, or at least the coefficient of friction, knowing a couple of constants. For that, we have the way in which we can plug in the angle of the hill, which we determined using a level and a GPS app, and the acceleration, which we determined from the time it takes to go from 0 to 10 miles an hour. And the normal force is also very easy because that's simply just the weight, since, of course, it has to go the opposite direction. Now, I know that having something as awesome as the Hobo lightning brings about a lot of questions, and as you can see here, I have many examples of what you might be asking. However, instead of answering them right now, I feel like the best thing I can do is just do a demonstration of how well the Hobo lightning works in regular transportation. So, to finish off this entire presentation video, here's some eye candy.
Alright, here we go. Here comes the speed.